So in this video, I just want to kind of explore the ideas behind the definitive integral a little bit more, or definite integral rather, a little bit more, and just kind of some properties associated with it. So first of all, a big key component here is that you can have negative area in this context, okay? So we often think of area as a positive thing, but when we're working with a function which has positive and negative parts, it should make sense that, we could have a negative area. So just to look at an example of this, let's consider the line y equals x minus 2. Okay, so it's going to look like this with an x-intercept of 2 and a y-intercept of 2. Okay. So if we want to find the integral from 0 to, say, 6 of x minus 2 dx, okay, we don't need any limits or anything like this, because notice that this is just making a triangle. So we can easily just do this using geometry. Okay, so this 1, 2, 3, 4, 5, 6. So maybe I'll extend this out a tiny bit here. Okay, so some of these points will be useful to have since this is just a triangle. So for example, f of 6 is going to be 4. So this is at 6, 4 right here. And that should be the only other point we need. So generally, if we want to find this area, we're looking for the area between the function and the x-axis. Okay, so that's what we were doing when we were finding the rectangles, right? We were stopping them at the x-axis and finding that area. So that's what we're doing here. Now, when it dips below the x-axis, we're doing the same thing, but the rectangles are going downwards. So they have like a negative height. Okay. So in this case, it's just going to be this area of this triangle, and it's going to be 1/2 base times height, like the normal area of a triangle, but that height is negative. So we have to take that into account. Okay. So this rectangle up here has width, it looks like 4, right? 2 to 6, and also height 4. So 1/2 times 4 times 4 is going to be 8. And then this one over here has length 2, but then height -2. Okay. So 1/2 times 2 times -2 is going to be -2. So naturally, if we want to find the area overall, we find the area of the two pieces and then we add them together, right? So we would get 8 plus -2 to overall get an area of 6. Okay. So we can have negative area in this context. Okay. Now, I only looked at the height being 0, right? What if we were to look at a variation of this? Same function. Okay, so we have x minus 2. And here I just want to look at 2 to 4, but I actually want to look at, 2 to 6, but I actually want to look at the integral from 6 to 2. So backwards of how we normally would write the intervals. Okay, of x minus 2 dx. So when we're defining our width, we're going in this direction, which is the opposite of what we normally do, right? So the width here, it's b minus a. B is this, in this case, is 2. So the width is going to be 2 minus 6. Like if we were making the rectangles, it would be 2 minus 6 over n, which would be -4 over n, right? So now the width is negative. So we do need to pay attention to the order of the limits of integration, because this is going to be a negative area now. Okay, so now we say that the width is -4 and the height is +4. So overall the area is -8 for this one. Okay, -8. So this does lead to our first property of the definite integral. Okay, so one property is that the integral from a to b of f of x dx is equal to the negative of the integral from b to a of f of x dx. Because all this essentially is doing is flipping the sign of your width. Okay, so it's just going to be the negative of the other version. Okay, so let's look at some other properties we could come up with here. So we'll just call this 1. What if the limits of integration are the same? Like a to a, for example. Well, then you can imagine that the width of your rectangle would be 0, right? No matter what your n was, no matter how many subintervals you had, your width would always be 0. So naturally, the integral here is always going to be 0. Okay. The area underneath the curve, it's like a curve with 0 width. So overall, it would be 0. Okay. So some of the other properties are just going to be kind of inherited by the fact that this is really just a sum and a limit, right? And we know about some properties of things with sums and with limits. Okay. So if we want the integral of f of x plus g of x from a to b, then with limits we could do these separately. With sums we could do this separately. So overall we can just do these separately. Okay, so f of x dx plus a to b of g of x dx. Okay. So the integral can be broken up over addition. Okay, just like derivatives could as well. And you could also have subtraction. So why don't I just write plus or minus in here? Okay, so subtraction is the same thing here. If we let c be a constant, okay, so just some constant number, then as we saw with derivatives, the integral of c times f of x dx is equal to c times the integral of f of x dx. So again, we can pull the constant out. So if we have, like the integral of 2 times x, we could do 2 times the integral of x instead. Okay, so this allows us to break it up into simpler parts if needed. Okay. And now this last one is about the limits of integration themselves. Okay. So let's let c, so not be a constant this time, but let's let c be some number in the interval a to b. Then the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Okay. So in other words, we can break it up over different parts if we want to. So we don't have to do the whole integral of the whole section. We can take it and look at just different parts of it. And we already did this, right? We did this with x minus 2. So here what we did was we broke it up as the integral from 0 to 2 of x minus 2 dx plus the integral from 2 to 6 of f of x dx, right? And I mean, it seemed very natural to do it that way when we're just working with geometric areas. So, working with a more, curved area or whatever, it doesn't change anything, we're still able to do that, right? We can still just find the area of individual pieces and add them together, just like you would for, other types of functions or figures or whatever. Okay. So this is a really helpful formula, especially the other way if you want to put them together into one large integral. Okay, so note that there's no multiplication property or division property. Like you can't necessarily say that the integral of a product is the product of the integrals. You usually can't. We do have some other, I said that was the last one, but this is kind of like another class of a couple of more here. So this one says that if f of x is greater than or equal to 0 on AB, so if f of x is positive on AB, then the area is also going to be positive, okay, on AB. Okay. So this should make sense naturally. Like if your function is always positive, then you're above the x-axis, so your area is positive, right? Okay. And that's assuming your limits of integrations goes from the smaller one to the larger one as well, which is what this interval notation implies. Generalizing this a little bit more, if f of x is greater than or equal to g of x on AB, okay, then the integral of f of x dx is greater than or equal to the integral of g of x dx, okay. So this one might be a little bit harder to show. I think that I asked you to show it somewhere. So there's a bit of a trick to it, but I won't spoil it. I guess I'm giving away that I think it's on something like a quiz or a homework or a test. I can't remember off the top of my head. But once you know this one, you can show this one rather easily, right? Because if f of x is greater than or equal to 0, then this implies that the integral of f of x is greater than or equal to the integral of 0, and the integral of 0 is just going to be 0, right? Because that implies that your height is always 0. So 7 kind of implies 6, and vice versa, which is kind of how you do the problem. Okay. And now the last one here is that if m and m, little m and big M are constants, such that f of x is bounded by these two numbers, okay, on AB, then little m times b minus a is less than or equal to the integral, which is less than or equal to big M times b minus a. So again, this should hopefully make sense if you just think about the definition of the integral. M would be like the maximum, f of x is always less than or equal to m, so m would be like the maximum height of one of the rectangles. B minus a would be the maximum width of one of the rectangles. So this is giving you an upper limit, the maximum height times the maximum width. And then this is the lower limit on the other hand, right? The still the maximum width, but the minimum height, right? So this gives us an upper and a lower bound for the integral. And that's actually more helpful than you might think. Oftentimes it's not exactly easy to actually evaluate an integral in practice. So oftentimes we're just looking for a bound on the integral if we can get one. Okay. In a probability and stats context, it's actually very helpful because your probabilities are always between 0 and 1. So if you show that the probability is greater than or equal to 1, then you know it's actually equal to 1. Or if you show it's less than or equal to 0, it's actually equal to 0. And a lot of probabilities are integrals. So this can be very helpful there.